I mentioned that you know, I have a bachelor's in chemical engineering. What I didn't say was, you know, my dad tried to talk me out of going to engineering school. I was getting ready to go to college. He said, Jim, you really need to go into business. Don't go into engineering. I wasn't sure what message he was trying to send me. Then when I graduated with a chemie degree, I was going into manufacturing plants, and he called me up again and said, Jim, you know your kids, right? You know your kids with their skill sets and capabilities, right? He called me and said, you know, the job you took down in Houston, manufacturing, you don't need to do that. You need to go into sales. Okay, don't go into the plants. And my plan when I came out of college was to spend a couple years working in manufacturing plants and then do design engineering, right? Design build. Well, I ended up spending 22 years in the plants, and then took over as director of engineering for a Fortune 300 company. But when I got that job, I sent him a note, and with one of my new business cards said director of engineering. I said, Dad, just want you to know I love you, but I don't always have to listen to you. Right? So engineers. Any Dilbert fans? How are your social skills? Blah, blah, once. All right, so this class is about really bringing science into the Bible and looking for contradictions, and they're not any, of course, but looking for how it complements the Bible, too. So did our world come about by chance? This is audience participation? This is no. Or are we the result of intelligent design? The answer, of course, is yes. All right, so let's look at things a little bit. Any guesses? We're going to look at one particular compound today. It was on the opening slide.
Water.
Water. Anybody here drink water? Yeah. Anybody allergic to water? It's not possible, right? It's part of life. All right. Before I get into that, let's talk about chemistry versus chemical engineering. Any chemists in the room? Good, that means I can say things with it. First of all, I'm going to go back for examples. The difference between an architect and an engineer?
Architect brings up stuff that engineer tells you it's impossible to do.
That's also good, but if an architect designs a building without an engineer, it might fall down. If an engineer designs a building without an architect,
it's not going to look pretty.
You're going to tear it down. Engineers are just been kind of different people, right? We were talking about that this morning with this Sunday. I had a professor in college tell me the difference between chemistry and chemical engineering is the difference between dollars and dreams, which I also kind of like, because we worry, chemical engineers worry more. Well, I'll come to that in a minute. Let's talk about chemistry as an example. Chemistry, the best chemists I've ever met, I've met quite a few good ones, they're kind of weird, okay? They really think differently.
As opposed to engineers.
They really think differently. They, I'll give you an example here. Anybody know what that is? Well, I labeled it.
The Sidewinder missile.
Thank you. Well done. Yes. Your powers of observation are incredible. All right. So you see this little tip here? Here. We used to make back in Roman house days. We used to make those things. Okay, and not the actual cone itself, but we made the raw material for that. It's not glass. In fact, they used to be yellow. They used to be about that big, and they were yellow. Very, very difficult to make. Okay, it was actually, you had to heat up two compounds, react them together, and as a gas, you put them across this plate and do it for 2 or 3 days until the gas it condenses and solidifies and makes up. The reason you can't use glass is doesn't. This is a heat seeker for infrared. Right? Sorry to bring weapons into class, but use it as an example. By the way, it's an Australian missile, not one of ours. You can't use glass because glass will only allow about 30% of infrared to pass through it. Okay, the same with plastic. So you have to come up with a compound that will allow infrared to pass through. The stuff we made did that very well, but it was yellow. So the federal government came to the company and said, look, love those products you have. Great, can you make it clear? And engineer said, no, it's yellow. Look, can you see? You can't. There's so it's a deep, dark yellow. You can't even see it. You couldn't see through it. Then one of the chemists looked at this thing and said, well, I think if you wrap it in platinum foil, stick it in the oven at 500 degrees C, let it cook for 2 days, it'll turn clear. No engineer ever would have come up with that. Okay, but the chemist understood that the color, yellow color, was some excess sulfur in the formulation, and that if he had platinum on the outside of it, the platinum would draw the sulfur to it, and the heating up just made it happen in days instead of years or decades. Okay, so chemists really think through that kind of stuff well. I'm not a chemist, I'm a chemical engineer. Can you go ahead and light the boiler for me? We're going to do we got a little show and tell project. It's a toy boiler that we're going to light up and get going. Don't burn yourself.
Should have got a stick lighter.
Sorry, I borrowed one. Don't be careful. All right, so chemical engineering. We deal mostly with physical properties: mixing, separation, pumping, heating, cooling, reaction, phase changes, that kind of stuff. Does that make sense to you? You get a lot of attention there. You're good. Got it going? Good. That's going to cook for about 5 minutes. All right, so let's talk a little bit about water, then we'll get into some of the unique physical properties of water that God created that allow life. First of all, annual planetary rainfall is about 121 cubic miles. That's 1 mile cubed times 121,000. It's like a lot of rain. We don't get that much here, do we? 78% falls at sea, which makes sense because how much of the planet is covered up by water?
70%.
Yeah. Most of the water's in the oceans, right? No surprise there. And how much of that's drinkable?
No.
It's all salty, right? And other stuff in it too. Got fish in it. Global evaporation, most of that occurs at sea, right? So that's where most of the water's going up. We're going to talk about the water cycle here in a little bit. The remainder comes from lakes and rivers and puddles and that kind of stuff. And even from your car, right? As your car engine uses fuel, one of the things that emits is water vapor, well, CO2. Here's an interesting fact I learned. Average time from evaporation to coming back down is 9 days, right? So the lifespan of a cloud from birth to end is about 9 days on average. Anybody know that one? Huh? Just checking the crew. All right. And water has the second highest surface tension. You guys ever have discussions about surface tension at your houses, right? About surface tension. That's one of the things you guys bring up. Well, some people do. You ever see a glass of water? You can slightly overfill it, right? Just a little bit, right? It makes a bubble on top. Actually, it makes droplets, right? That's what water vapor. Sorry, water does. High surface tension. All right. I'm a little fast. All right. Water's mentioned in the Bible 772 times. So I didn't count it personally. I used Bible word counting. First mentioned in Genesis, of course. The earth was formless and empty. Darkness covered the deep waters. The Spirit of God was hovering over the surface of the waters. Would you want to be there and seen that? Wouldn't that have been amazing?
But it was dark, right?
It was dark. Yeah. If you had infrared capability. In Genesis 1:20, God said, "Let the waters bring forth abundantly the moving creature that have life." Life comes out of the water, right? I'm not saying we evolved from water, right? The humans, but life began in water. That's what the Bible says. All right. Lots of biblical events, right, that have water mentioned in them. Let's name some.
Baptism.
Baptism, yes.
Water and wine.
Water in the wine.
Parting of the Red Sea.
Part of the Red Sea.
Water to blood.
Water in the blood.
Noah's Ark.
Noah's Ark.
Like the woman at the well.
Woman at the well.
The lady washing Jesus' feet with her tears.
Good. Feet with tears, right?
Jesus walking on the
Jesus
water.
washing feet too, right?
Jesus walking on the water.
Jesus walking on water, right?
Or Peter walking on the
You guys came up and read more than I did, right? John the Baptist, Psalm 23, right? Leads me beside still waters. Jesus on the cross, side pierced, right? Water coming up, blood and water. Red Sea, Rita Cain, and Noah laid it well. Here, you guys think like me? You guys think like engineers. I'd be very worried if I read. All right, who remembers this?
Yeah.
Boy, did I hear a lot of groans out there. We're just going to look at one. You guys remember what this is, right? This is the periodic table for chemistry, right? You see hydrogen up here? Oh, so let's go back a minute. Hydrogen is up there, right? What's water made up of? H2O. 2 hydrogens for every oxygen, right? You see oxygen? Right? Row 16? Group 16? Now, you remember how they created the periodic table? Yes? You know, we all know that, right? That's why I don't have to go. Let me go through it. Just maybe there's one person who forgot how it happened.
It's been a long time since I.
I know, I remember it, but just for the sake, I want to see if you know.
10 stars. They took all the elements and they grouped them together based on electron shells, okay, on how many electrons they need to finish off their orbitals. So if you look at the far end, they call those the noble gases, the heliums, the neons, the argons, kryptons, right? They don't react with anything, the electron shells are full. If you look at group 16, which where you have oxygen, sulfur, selenium, telluride, et cetera, they all need at least, they would need 2 hydrogens to finish off and fill their shells up, okay? Clear? No. Clear? All right, so let's look at some physical properties of hydrogen with elements in group 16. Isn't this fun? Oh, come on, get up there. There we go. Don't you enjoy this? Don't you going to learn something in this class? Right? Right. Let's look at boiling points. All right, so we're going to make our hydrides. We're going to take those compounds, go back them again, right? Oxygen, sulfur, selenium, and telluride, and react them with hydrogen. Right, so you'll have H2O, H2S, H2SE, H2PE. Okay, clear? Got it.
Oh, question.
Yes.
If those groups in that need 2, the ones that are, say, in 17 just need 1
One.
hydrogen?
Yes.
And then the other ones on the other
We
side
need
need
3. That's why ammonia is NH3, or hydrogen fluoride is HF, hydrogen chloride.
Gotcha.
Got it. Next. All right. Now here's we can measure this. As you look at the boiling points of hydrides, as molecular size decreases. Molecular size is you take it. You can cover that. Where did I put this chart on there too? As the elements go down higher, they get heavier. Okay, they get more. There's more, but there's more to them. There's more mass associated with them. Okay. Oops, sorry, wrong way.
And the ones above them are more excitable and or
They're lighter. You can't say more
lighter.
excitable. It depends
they
on.
want to find something to grab onto.
Yeah, they want to react,
Yeah,
right?
they
If they're
want
by
to
themselves, they
really-
want to react. Sometimes it's just with themselves.
Right.
Okay.
Right.
So let's look at hydrogen telluride. Who thought telluride was just a place you went skiing? Okay. Not something we use much of. Okay, so it has a molecular weight of 54, and it boils at -4. So what is it at room temperature? If it boils at -4 degrees C, it's a gas. Okay. And remember, we're going up the chart, right? Hydrogen selenide is lighter. It weighs 36 grams per mole. Okay. And where's it boil? -42. So we see the trend, right? As molecular size decreases, the boiling point gets lower and lower. So hydrogen selenide at room temperature is also a gas. Hydrogen sulfide, very poisonous gas. Don't read this. Not good. Sorry?
Bad guess.
Bad gas, right? It will kill you.
H2S.
Breathe it in, right? Molecular weight of 18, right? It's a gas. Boils at 62. right? Now we take oxygen, take hydrogen, react it with oxygen, right? That's going down, that's going down. Uh-oh. Hold it. What happened there? It got smaller. Well, the boiling point went,
Wait.
what's going on?
You're
God?
about to tell us.
I'm sorry?
You're about to tell us.
Well, okay, so scientists have gone into this, actually chemists and physical scientists have gone into this, and they understand that the hydrogen bonding is what creates that difference, okay?
Are there double bonds there?
No, singles. The dipoles, how they react, both sides of the molecule, but the dipoles. So hydrogen bond is what's the cause of that, right? Here's the thing, God gave us dominion over animals. That'll be my last quote. He didn't give us dominion over physical properties. God kept that to himself. Okay? God created that. Okay? That's why water at room temperature is a liquid. And you gotta put a lot of heat into it to get it to boil, right? We'll talk more about that in a minute. You see, isn't that amazing how even in the periodic table, that's a big, huge difference that came out through there. Right? From minus 62 to 100 degrees Celsius, where it should have gone the other way. Design. Not accident, design. All right, more we talk about boiling point. Let's talk about freezing points. Think of there are some. Can you think of any non-carbon material that's a liquid at room temperature?
Is it like H2O2, like hydrogen peroxide?
Yeah, that's still water.
I'm
That's
being
still,
easy on that.
yeah, think, mercury. Mercury is one is a liquid at room temperature. Right, but just about everything else, all the other liquids are going to have carbon in them in some form or fashion. Acetic acid, version of wine has that. That's kind of a neat chemical too. We'll talk more about that in a minute. And when you freeze a liquid, most liquids, when you freeze them, they get more dense. Okay, right, and then they sink to the bottom of the liquid. Okay. You've seen that before, right? I mean, if you freeze anything else besides water, what happens with water?
It floats.
It floats. Right? Ice comes to the top. Right? Did you ever think what would happen if it didn't do that? What if we had a lake and ice froze onto the bottom?
There would be no hockey.
Is that a good thing or a bad thing? No hockey. How are we doing that?
Squish on the bench.
Would never
We
melt.
kill the animals.
Yeah.
Squish on
That's not quite ready yet. Right. It would kill all the animals, right? So all the undersea, all the things that fish feed off of, and all the stuff all below them. If lakes and ponds froze from the bottom up,
And they would overflow.
then it would overflow
Some of the ponds would.
because
The ice would overflow the pond, depending on how full the pond is.
Okay. But really, if you look at it, if ice did freeze and go to the bottom, or started freezing at the bottom, works its way up top, fish as we know it, all the undersea life wouldn't exist any longer. So ice, because it floats, it actually acts as an insulator and allows warmer temperatures to be below, right, where things can survive. An accident or design?
Design.
It's design. It's got to be design. By the way, are there any liquids that do that operate that way? Acetic acid vinegar does that. I was going to say that. I missed that one. It's probably okay.
He said he was going to say that. Yeah, right.
And why? I know God designed it that way too. I can't tell you why. Oh, we covered that. All right, so let's talk about the water cycle. You guys have all studied this, right? And you guys know all about the water cycle, right? Okay, there's a song that goes by. I don't remember the song. Is there?
Evaporation, condensation, precipitation, falling down.
There we go. That was impossible. But you guys have learned about this since when? Since grade school? Right, so how long have we known this fact? Forever, right? We've known this forever? Not so. It is in the Bible. We'll talk about that in a minute. Right? Until the time of the Renaissance, it was believed precipitation alone was insufficient to feed rivers. Underground water pushing upwards from the oceans was the main contributor to river water. Bartholomew of England held this view, as did Leonardo da Vinci, 1500. First published thinker to believe that rainfall alone was sufficient for the maintenance of rivers was Bernard Palissy, 1580 CE, 1580. He's as a modern theory of water cycle. But not proven until 1674 to another Frenchman. By the way, I learned 5 or 6 years ago, I'm part French. I'm still depressed about it, so please don't.
Don't give up.
A small part, it doesn't grandmother's side, but it is there. All right, but really, till the early 19th century, that's what people believed, right? That the oceans, underground rivers were part of this. That we now know that's not the case, right? It's all just coming in from evaporation and precipitation and all that kind of stuff. How are we doing on time?
15 minutes.
All right, so what we have over here is a toy for chemical engineers, because we lit a fire, well, he lit a fire under the boiler. Boiler's making steam, right? And steam is going to push that little engine, a little piston, and then it's a toy I picked up with Kathy. We were shopping in Pennsylvania before Christmas. It's a toy, in the 1950s toy, okay? We were talking before, you can't possibly, can you imagine giving a toy like that to a kid today?
Kids were men.
Almost there. Almost there. I'm not going to cover this French guy. The reason I put this in here was he was a Protestant back then. Back in the time when Protestants were persecuted. Catholicism was the rage at the time, and Protestants had their property confiscated, and folks were thrown into jail for their beliefs about going against Catholicism. He ended up dying in jail, actually. All right, so there is another history of water cycle. Any guesses? And Joe? He draws up the drops of water, which distill as rain to the streams. The clouds pour down their moisture, and abundant showers fall on mankind. Does that sound like the water cycle? So why did we not believe that at the time, back in the 1800s? How did we miss that?
Because they didn't read the Bible.
They didn't read the Bible. They couldn't read it. Yeah, they couldn't read it, didn't have it.
Well, how many clues of intelligent design are there now that we read every day?
And then there's still people that don't believe it.
I mean,
They think it's just a work of epic poetry, they don't think it's inspiring, Joe.
Yeah, it's not, well, they won't call it fiction, they'll think it's allegories, right? Or
Well, it's a
mythos, yeah.
poem because it follows like an acrostic, like a pattern, but that's what people think.
Yeah, well said. Good done. All right. So surface tension again. Let's come back to surface tension. Mercury has the highest surface tension. You ever play with mercury? You really shouldn't. You ever play with mercury? Right. You see little drops roll around. They're kind of fun. Like we're breaking thermometer. You can still buy mercury. You can still buy it, but vapors aren't good for you. So I'm not recommending it. Okay. You know, I play with toys like that.
Yeah,
I'm not
rock your
recommending.
bowler and play with fire.
Good, it's been wise. This thing should be cooking big time right now. There we go. Make sure that fall table will get going pretty good here in a minute. Oh, we can even make it do a little whistle. See, that's a chemical engineer's dream. That little toy has so much in there to learn from. All right, surface tension. Who cares about surface tension? Hmm? You do. You care about surface tension? I guarantee your animals care about surface tension, water. We'll talk about that in a minute. Right? It allows them to be able to drink a lot easier than they could otherwise, right? I was guessing some of you may not know what surface tension was, so we'll just talk about that in a minute. It's a measure of the force necessary to stretch or break the surface of a liquid, right? How much that you have cohesion of that, right? Water behaves as if it's covered by invisible film. You ever see a water strider, right? And see how they dance across the water, and you wonder, how do they do that, right? They're so light, and their feet are spread up enough that they can actually rest on top of the water. So surface tension allows you to overfill a glass. You ever see ants carry water?
Mm-hmm.
See the water film coming across his head, right? Right. Well, that wouldn't happen with any other liquids, right? Wouldn't happen with gasoline. Wouldn't happen with. Well, that's normal. And also animals, right? When they're drinking, yes, their tongues can create little cups, but also they get a much thicker layer of water on their tongue because of surface tension. Okay. They can get about 2 or 3, some animals, 2 to 3 times more liquid because it builds up that film that you see on the guy's head. Okay. So, surface tension. Accident or design?
Design.
It's got to be design. All right, some other unique properties of water. Water is called a universal solvent, right? It's not universal. You can't dissolve everything into it, but you can dissolve a lot of things into it, right? Example, what can you do? Salt? Salt water goes into it. One thing, back on surface tension. How do you break surface tension? How do you decrease it?
Soap.
Soap, surfactant. That's right.
It makes water more wet.
Yes, right. If you're putting down we have a crop person here, right? Yes. If you're putting something into the ground, you want to make it water, right? So you add.
What's more on a leaf of plants that you're trying to kill, you want to break that surface tension so it'll spread out over the leaf.
And how do you do that?
With surfactants, adjuvants, to break that surface tension.
When I work at golf courses, same with pesticides. We put a little bit of soap into the mix and then go across as we treat it, and then we penetrate further in the ground and kill more insects. Right? How do you make soap?
Horses to,
Sorry?
you can haul your old horses to the kill plant.
I'm planning on going there.
They used to make soap that way.
But you can make soap out of fats, right? And take the ashes from a fire and make it. It's pretty simple to make soap. I've done it. Pretty simple to do. If there was a chemist in the room, I call it a saponification reaction, but there's no chemist here, so you can't go through that. So water dissolves. You can dissolve a lot of things in water, right? You can dissolve oxygen in water. Right? If you couldn't dissolve oxygen in water, fish would have one heck of a time, right? All the animal life under the sea and under the ponds and what have you. Water also takes a lot of energy to heat it up. Okay, this is also a big deal. So I'll use an example. It takes 4.814 joules of energy to heat 1 gram of water 1 degree centigrade. Okay. That's not like a lot. You guys ever think in joules? Measure energy? Yeah, see, engineers do that kind of stuff. All right, so take copper, right? It takes less than 1/10 the amount of energy to heat 1 gram of copper up 1 degree. Big difference, right? That's why if you go to the coast, that's why you get more moderate temperatures, right? In California and Pennsylvania, not Pennsylvania, not coastal, Maryland, East Coast, West Coast. Those temperatures will moderate based on the water temperatures are there. Water is also, the evaporated piece also gives a great cooling, right? So the sun's always heating the earth, right? Heats all that water, and what happens? That water starts evaporating, right? It provides a massive cooling effect as well, too. Accident or design?
Design.
Yeah. All right, so what power has God given us? Genesis. And God said, let us make man in our image, after our likeness. Let them have dominion over the fish of the sea, and over the fowl of the air, and over the cattle, over all the earth, over every creeping thing that creepeth upon the earth. So God created man in his own image, in the image of God. He created he him, male and female, created he them. God blessed them, and God said unto them, be fruitful and multiply, and replenish the earth and subdue it. Have dominion over the fish of the sea, over the fowl of the air, and over every living thing that moveth upon the earth. You guys know this verse, right? God gave us power over all living things. He kept control of physical properties. Right? So all the things we just talked about, the boiling points, surface tension, freezing points, what things dissolve into what and what doesn't, God controls that. He did not give that to man. He kept that for himself. And sometimes he made some unusual tweaks in the design. Okay, you look at the boiling points of the high drives, for example. He tweaked that for water, so it would support the rest of the life we have here. We don't have that kind. We can use physical properties. We can manipulate them. We can do engineering things and take a gas and turn it into a liquid, or a liquid into a gas. We can react things together. But those physical property things, those are man-made. They're things that we study and learn how to do. But it's not something that we can manipulate whatsoever. Can we manipulate gravity?
No.
If I drop this, it's going to fall every single time. Right? God created that as one of the physics, one of the things that's a physical property piece. Can I take hydrogen and react it with neon? I can't. Right? It's just never going to work. No possible way. It's not a design that God gave. To give you a little different sense of what water means to us and how God set this up, that we have a pretty neat planet to live on.
It's not an accident that our planet's 70% water and our bodies are too.
Good point. Was the show and tell useful to you? What's to give you a sense for it?
Absolutely.
How many people want to be an engineer now?
I just want one of those.
How are we doing time-wise? Can I share one more chemical engineering story with you? This is a disaster that happened in my past. Remember we talked about liquids. As they get colder, they get besides water, they get denser and actually fall to the bottom, right? I was working in a plant in Tennessee, and Kathy and I were visiting my parents over Thanksgiving, and I got a call from the plant saying that, hey, we had some pipes burst. They were doing some maintenance work. Again, we're using organics. So we were making a herbicide, STAM herbicide. And the raw material was dichloroaniline. Anytime you have chlorine in a chemical, it's usually not good.
Yeah.
Okay. And this stuff is normally stored as a molten liquid, but because we were doing maintenance work, we turned the heat off, and the stuff cooled in the pipes and condensed and became solid. Maintenance work was done, turned the heat back on, all of a sudden we popped a whole bunch of gaskets. The stuff flashed over the entire 3-story apartment building, left a coating of very, very toxic crystals. The actual compound was tetrachloroazobenzene. One little bit anywhere in your body would give you permanent acne. It was a $2 million cleanup for that little offense. Never even saw that as a possible hazard at the time. I told Kathy after that I'm going to get fired. Yeah, I ended up getting promoted, so it's a disaster.
Must have been a government gig.
Or a bank gig.
All right, hey folks, thanks for your time this morning, and